All right, everyone, let's get started. Can we confirm you can hear my audio? All right, thank you, everyone. Hello, my name is David Rock. I'm in the University of Maryland in Baltimore, here in Baltimore, Maryland, and welcome to Cytometry in R. And this week we're taking a look inside what's inside an FCS file. So I feel a little guilty after subjecting everyone to two very R-focused lessons for the last 2 weeks. So I wanted to add in a little bit of flow cytometry focus, so this is why we'll be looking at FCS files. So hopefully I want by the end of today that we kind of have an idea of how an FCS file gets represented within a R object known as a flow frame, so that we're able to work with these flow frames a little bit better when we need to retrieve certain information in the context of R. Namely, if we're trying to get the MFI values for a particular fluorophore, if we're trying to access some kind of metadata, these are the things that having a little familiarity with how those particular files are structured will be particularly useful in the long run. At the same time, we are gaining additional exposure as far as object types in R. So in context of like the last 2 weeks, the very first week we tackled one of the beginning coder challenges in terms of how to install packages. Last week we tackled one of the second challenges we often encounter, which is how to direct a file path to our FCS files. Early on, when you're first starting to learn how to code, one of the things a lot of people will struggle with is trying to figure out what kind of an object is a certain thing we have created. Because basically, if we're still continuing the analogy that we had for the last couple of weeks, where functions are basically tools, a package is basically a toolbox, just like there's different kinds of tools. If you think there's hammers, there's screwdrivers, there's paintbrushes. All these different tools need different kinds of objects in order to do their work. So if you're working with something that requires a hammer, you're going to need a nail, you're going to need some boards. If you need a screwdriver, you're going to need some screws and a pre-drilled hole. If you're working with a paintbrush, you're going to need a wall and paint. So it's kind of similar when you're working in R. You don't want to hand a paint bucket to the nail because it's just not going to work, and vice versa. So one of the things I'm going to emphasize throughout the early portion of this course is just trying to keep a familiarity of like what are the main types of objects, which I started looking at last week when we were working with vectors, and we are trying to see, is this a vector that's containing character values? Is it containing numeric values? Is it containing logical values? And we're going to build on that throughout today. The challenge is going to be flow frames are relatively complicated objects. So I'm going to have to take you to the polar opposite side. Instead of being very simple objects, we're going to look at a very complicated object and then see all the little bits and pieces that make that complicated object work. So today, as far as housekeeping goes, we are building off topics that we covered during the first 2 weeks, namely how to install our packages and then how to do file paths. I know some of you came into the course not having very much flow cytometry experience. If you're in that camp, I still recommend the University of Chicago's Flow Basics tutorials. They'll help you get some of that additional context as far as like why do we care about certain flow cytometry vocabulary as you go. Now, the main thing for today is if at any point you encounter a situation where you're like, I have no idea what's going on, please just feel free to take a break and circle back a little bit later. So the goal of today is not to memorize the 100 archaic keywords that we can find in the description list of a flow frame. That's not the point of today. We can always search those when we actually need them. But the main focus of today is still building additional familiarity with these concepts that we're working with in R, but also to highlight a typical object exploration workflow. So don't power through, don't force yourself through it. If you just can't hear about another keyword, circle back later when you're actually in an exploring mindset. So one of the things I kind of would like everyone to do is picture like some kind of information that you personally would like to be able to retrieve from an SCS file. And as we go through today's lesson, just kind of like see how we navigate, how we explore, and how we go through those different paths until we eventually find that information that we need. Because this is the same kind of coding mindset that you'll be building slowly with time throughout the course. And this is kind of like what I'm trying to do for today, just as far as introduction in a semi-controlled manner as far as like what we are looking at together as a group. And as we do every week, there's new data sets that are now available on GitHub. So if you haven't actually synced your forked version of the Cytometry in R project, I encourage you to do so. Once you have done so, kind of similar to what we did for that first part of last week, pull it locally to your local computer within Positron using the pull feature. And then at that point, copy the data that you need over to your own project, working project folder. If you want to create a new one, kind of like what we did last week, call it week 3. If you want to reuse last week's, do the same. But just remember to commit the changes that you have done and push them back to GitHub so that worst case scenario, you're still maintaining version control as you go. And with that, let us begin. So, I'm going to assume we're working in the working project folder, regardless of how you've named it. I kept it as week 3 for my end. But the very first thing we need to do is we need to find an FCS file, and we need to specify our FCS file path. So if we're retaining the same kind of structure of the project that we had last week, it would look something like this. So all my little FCS files are currently within the data folder. It's within our working directory. So I'm using the file path function to basically specify, hey, look within data, and then handing that off to my computer as the file path, which I'm calling as the object path to data folder for today. At that point, we can then use the list.files function that we saw last week. And as we saw towards the end of last week, we need to set the full.names argument to true, which will allow the full path to be listed, which allows us to actually find our FCS file. So in this case, it looks within this particular file path. It lists all the files that match this pattern.fcs, and then it returns that list of files to this object, which we're calling FCS underscore files. And as you can see, this is the full path to my one FCS file that we're working with at this point in time. So similarly, if we had left full.names equals false, as we saw last week, you'd see we're not including the full file path. The location that this file is in, data/cell counts, is no longer there. We're just saying the actual name of the file. And this is similar to what we saw last week if we had run the base name function on that full argument for FCS underscore files. It would just return the actual file name, not the location as well. So today we're going to be working with FlowCore, and this is one of the oldest flow cytometry packages on the Bioconductor project. It's also the most frequently downloaded because a lot of things depend on it. So this is not the best way to visualize this particular graph. Check the website if you want to see it. FlowCore is all the way down at the bottom, and this is basically all the different, if my screen will stop glitching on me, it's all the different existing packages that are on Bioconductor that are flow cytometry related, and you can just kind of hover and get the interactive features and see how they work in a particular year. It's kind of cut off right now in this Reveal.js slide. Check the website for the full feature. But FlowCore has been around for quite a while, so if we actually go over to the side, we can see that FlowCore is this dot right up here. And it has over 26,000 or so downloads every time Bioconductor refreshes and upgrades to a new version. So everything else as far as packages goes is very, very much lower in terms of total number of downloads, and it's much, much younger in age. So it's not like heading on 20, it's over on the other side. Also, if you're seeing the screen flicker, please let me know in the chat. It's flickering on my end, but I don't know if it's actually affecting the stream on your end. So if you do see issues with the screen flickering, please let me know in the chat so I'll try to resolve it. It's not, however, idle power true, assuming it's just my HDMI cord glitching and it's not affecting the stream. So FlowCore is one of the many Bioconductor packages that's maintained by Mike Jung, and in many ways, all the work that he ends up doing for the Bioconductor project reminds me very much of this XKCD comic, where all the Bioconductor flow cytometry package infrastructure is very much a project that Mike and his collaborators have been thanklessly maintaining since 2007. So FlowCore itself does a lot of the heavy lifting, mainly because it's what defines the flow frame objects that we use to store the FCS files into to make them available when we're trying to use them in R. So, as with everything, when we're trying to use a package, we need to attach it to our local environment. So as we saw during the very first week, we need to use the library call. So in this case, let's go ahead and do library function and then the name of our particular package that we want to load. In this case, remembering we don't need those asterisk marks. And then at this point, what we're going to be working with today is the read.fcs function. And do you guys remember how to look up the help documentation? If you do, there's this little drop down. And as you can see, once we have loaded it in, if we're within a code chunk, we can do $flowcore, and then that will pull up the actual function name itself. Alternatively, if you're within positron and working within a code chunk, you can just hover over the function name and it should pop up the help documentation. So at this point, we have found our FCS files of interest. We need to first go ahead and index the very first FCS file that's present. So the way we do this, remembering back to what we saw last week, is basically within those square brackets, we put the position index of whatever particular file we're interested in. So for today's example, there's only one we're actively working with. But if you're doing this with your own files, you may have multiple files. You may want to compare between your files. You can specify the index and get back a particular file that you want to work with. So in this case, I'm specifying I want the first file within FCS_files, and I'm assigning this to a new object, which I'm calling first file. Now, when we're working with read.fcs, it has several arguments. The main argument is file name, which is where we provide the file path to the location where our FCS file. So if we're actually writing it out, we'll see something like this, read.fcs, and then within the parentheses, the actual file name, and we're assigning the location as the file path that we're interested in. Now, if you actually see this function in the wild, you'll never see it written just as is, because there's two arguments that are very important when it comes to reading in our own data. And that is transformation is always set to false, and truncate max range is also set to false. The reasons behind this we'll cover in week 5, but then also touch on it in a little bit. But if you're trying to follow along at home and you want to be able to do data analysis with your own, just remember to include these two arguments. And what happens when we actually go ahead and run that line of code with these arguments set to false is we have an object that gets created. And as you look at it, you can see it says flowFrame object, the name of our particular file. It lists the number of cells and 61 observables. And then it gives us a couple of columns, which we'll go through in just a second. And then if you scroll all the way to the bottom, you can see 476 keywords are stored within the description slot. So in this case, what we have read into R is not actually the FCS file itself. If you're working within positron and you click on the FCS file within a data folder, you'll see all these little, it's not read properly within positron, you'll see all these little star icons. So what we're working with is what's known as a flow frame. And it's basically how all that data contained within the FCS gets read into R in a standardized format with which we can work. In addition to number of cells and number of columns, the number of columns which we just saw right here, the names themselves will also depend as far as like, are we looking at raw spectral flow cytometry files, or are we looking at unmixed spectral flow cytometry files, or we're looking at conventional flow cytometry, and then mass cytometry files are a little bit similar in that regard. So the very first one I want to point out is the 61 observables. So in this case, I was working on one of the auroras. So what we're looking at in this case is, I believe this was our 4-laser aurora that we were working with for this particular file. And the 61 observables kind of corresponds to the total number of detectors that are present on our Cytec aurora. The number of cells, I had downsampled this FCS file, so it wasn't taking up much of your computer memory. So in this case, there's only 100 cells that are present within this flow frame object. And I think that was the explanation for this one here. And then at the very bottom, we basically see there's up to 599 keywords within the description slot overall. So this is just what we've read in so far. This is just a representation of our FCS file now that it's brought into R. The question now is, okay, we have an object. How do we actually go about trying to decipher more information about this? And how do we like model? You have a new object, you created it, but you don't know exactly what it is or how you can use it. How do you go figuring out what kind of type of object it is, what kind of inputs does it take, etc., etc. So within our bearings, at this point, we have loaded in the FCS file. We need to use some of those concepts we had last week in trying to understand how it works. So from the output, we saw it listed for a flow frame object. So let's try reading it back in, again, the file. But this time, let's assign it to an actual object that we create so that some of those type discerning functions that we used last week, like str and class, we can actually call them on the object and be able to use them. So in this case, let's just read in the FCS file, and let's assign it to the object we're going to call flowFrame. And as we read in flowFrame, we can now have it pop in. If we look at our right secondary sidebar, we can see the object is now visible. And within positron, it'll give you a little bit additional information. So in this case, you see flowFrame under the value. You can also see an S4 class flowFrame, package flow core with tree slots, flowFrame, etc., etc. So if we were trying to use our type determining functions that we learned about last week, we use the class function and call it now on that created object. And as you can see, it gives back some somewhat similar information. It tells us it's a flow frame type object, and this is the actual specifications of what a flow frame is and how it's composed is given by the flow core package. So flow frames are a class of objects that are defined within the flow core package. They are used to work with the data that's contained with our individual FCS files. However, as we're looking at that right secondary sidebar, what we see is appearing is that S4 flow frame package flow core with tree slots, words flow frame next to it. And the absolutely perfectly valid first response to this is, well, how should I know what any of this means? So this is perfectly reasonable. Oftentimes, bioconductor packages have very archaic, big objects. So we need to power through this initial set of discomfort and just kind of go ahead and start exploring within positron using those little click on drop down arrows that are next to the variable name so that we can kind of get additional information about what kind of object are we working on. Is there any additional structure? Is there additional data that we can actually get out of it? So if we do this in this case for flowFrame, if we come back up here and we are clicking down on that little drop down arrow under the actual name, you see this tree slots is kind of like appear at this point. So we can see one of those slots appears to be expers, which we can see is showing up as 100 rows and 61 columns with a matrix. You see a parameter, what appears to be a parameter slot with something more complicated that just gives us an initial set of discomfort. And then we see description, which starts listing things that, at least if you have some flow cytometry experience, kind of makes you think it might be a keyword of some form or another. So at this point, we've inferred that those tree slots must be kind of corresponding to these tree objects that we see when we do the dropdown. So at this point, flowFrame is basically our first encounter with what is known as an S4 object type. These are very complicated object types. They're more common within the bioconductor affiliated packages, but they're still very much kind of like a tool. So if we were like working with like hammers, paintbrushes, screwdrivers, this is more on the range of like you're working with a vortex or you're working with like a small cell counter or something like that. It still does a relatively narrow focus as far as what it does, but it's a little bit more complicated and it has a little bit moving parts. So we're not actually going to dive into all the details of how to create these. That's a very later in the course discussion. But I just want you to be aware that when you see something that's S4, it's likely to be a little bit more specialized in what it does and how do you interact with it. So as we go mostly it's the same description of what I did, you'll also occasionally see an S3 object in this sense. So the advantage of why people will use S4 and S3 objects is basically you can kind of bundle things together. So instead of just having just the FCS files MFI data, you can also have the metadata attached within that same object. So that's the main motivation behind why people use these objects. So let's tackle that very first slot within the flowFrame object, which we saw was named expers. So we already had some basic information about it. We can gather that it has 100 rows, and it has 61 columns, and that is a matrix style object. So it's kind of very similar to this output we had when we first ran the read.fcs function, where it told us some of this information as far as 100 cells, 61 observables. So at this point, we can kind of infer this expert slot is likely what's going to be containing the MFI values for our flow cytometry file. So within positron, if you're working with something that is table-like or like a grid, there'll be a little grid symbol that appears on the very far right of your screen. And this is always my favorite thing to see, which means I don't have to do quite as much exploration. I can just click on it and it will actually open up the underlying data. So in this case, let's navigate to where we have the experts. Let's slide all the way over to the right and just go ahead and hit that little grid. And what's going to happen is basically it's going to pop up on our editor window. And we're going to have a scroll bar that allows us to both scroll across to see what all the different columns and all the different names associated with those columns, as well as scroll down to see all the individual values for every cell. So this is kind of what you'll see when it actually pops up in your editor window. You can see the column names are present, so you can see its time and each of the individual detectors, because this is a raw spectral flow cytometry file. You can see if you scroll all the way down, this goes down to 100, so it's corresponding with each row is equal to the measurements for one particular cell. And one of the nice features within Positron, it kind of gives you a little summary table on the side, which can kind of help you get a general idea as far as like how the particular data is distributed in terms of, is it really large values, is it really small values, do you have anything missing? This is kind of like one of the nice things about Positron as far as what it's able to show you. So at this point, we have seen the matrix, but we haven't actually extracted it out and placed it within an object that we can then come back to and work with later in R. So let's go ahead and do that. Basically, we're going to be assigning this to a new value. Since this is within an S4 object, we can't use any of those accessor functions that we've used before, like square indices or all those different variations. We're going to need to be able to access it within the S4 object. And the way you access a slot within an S4 object is you use this little @ symbol, and then you give the respective slot's name. So what this looks like in terms of code is we have a particular object, which is the flow frame, which contains all the information about our FCS file. But we only want to grab this experts matrix from that flow frame. So what basically is happening is the experts matrix from the flow frame is then going to be assigned out to this MFI matrix, which is going to exist within our environment. So at that point, we don't actually have to go back into FlowFrame to get that same set of data. Alternatively, Bioconductor also has helper functions that kind of do the same process, but cut out the little @ symbol. So in this case, if you're trying to get at something within experts, you're using an experts function, and then you're just providing the actual name of your FlowFrame object, and it will go ahead and do that same exact feature of grabbing out the MFI data that you're interested in. So in this case, we have 100 rows, and as we saw with my attempt at the interactive image a little bit earlier, it's going to quickly overwhelm what we have as far as screen space. So it's oftentimes good if you're working with a matrix or a similar object, which is known as a data frame. You want to subset what you're actually displaying within your console window at any point in time, so it doesn't get too overwhelming and you lose track as far as like what code you have actually run. So the way you would do this in R is you can use the function that's known as head, and then you just basically say, this is my matrix, and then with a comma, you specify how many rows do you actually want to visualize at any point in time. So when we run this function like this, you can see I have the first 5 rows for the however many columns this is. And then if this was displaying out to your console window, you would see the next part repeated, and you see, once again, it's the first 5 rows for these other sets of columns. And same thing continues all the way down until we hit the R8 detector for this Cytic Aurora. So this is useful, especially if you don't want it to be massively overwhelmed what you're seeing in all in one go. So now we were just seeing the matrix itself, and we saw that there was associated column names for each column. But what if we wanted to retrieve those column names so that we're able to work with it? If we want to subset which actual markers we're interested in, which if we don't want to include the side scatter or the time parameter, how do we get about the information as far as like what the columns are called? So within R, there's this function we call column names, and that will do that exact same function that we want. So all we need to do is, now that we have this matrix extracted out from the flow frame object, we can run it within the column names function, which is going to retrieve values, which we'll see end up printed like this. Now this initially looks a little bit different from what we had last week when we were working with the floor object, where it was BV421, FITC, PE, and APC. We have these weird numbers, a $, P, a certain number, and then an N right afterwards. So this is a little bit confusing as far as what's going on. So let's try to figure out what's going on here, why we have this extra set of information beyond just the column names themselves. And click here. So if we're looking back at what we had for the read.fcs function, we see we do have similar objects listed on the side. So name is corresponding to basically what we're seeing for those column names. But then those kind of numbers that we're seeing on the side kind of do match with what we saw when we did grab those objects. So we think they might be somehow trying to like refer back to them. But this is one of those things as you first start exploring an object, you're not going to know directly off the bat. So you're trying to infer, you're trying to triangulate like what's going on, what's the purpose of these things as we move forward. So let's go back to what we do already have. We know we have the str function and we have the class function, which will kind of tell us what kind of type is this particular object that we're working with. Let's try to run this on those objects we have just extracted out. So in this case, if we go back to column names and we run str on it to see what kind of type of object it is, you see it comes back a little bit different from what we had seen before for the floor object last week. We still see it's a character value. We see it goes from 1 to 61, so to 61 columns. This part all looks very similar. But what we see is also there's this named portion directly in front. And then right underneath it, we get a line that says attribution names. And then we see those names are being listed at that same point in time. So by contrast, when we were like looking at it in terms of last week, we didn't have this name characteristic. So somehow this type of list, this type of vector appears to be a named list. Let's go ahead and check that other function we learned last week, basically a class, to see if we get any additional information. And in this case, if we had done it, we see that class column names doesn't actually provide us additional info. It just tells us that it's character. So this is kind of highlighting why we should always try stuff with like at least 2 approaches. So using str, we got a lot more information than we would have otherwise, versus if we had just run a class, we would have thought, oh, this looks exactly the same as that vector we had last week. So in terms of like when you find something odd and you're trying to troubleshoot what's going on, just try to get a couple lines of evidence as far as like what this object type may be, just to make things a little bit simpler for everybody. So at this point, we know we are working with some kind of list because we have our individual detectors being shown, but it also appears to be names. So if we just wanted to actually have the values of the column names themselves, not all the actual name associated data, what we could use is this new function, which is the unnamed function, and it works on those named vectors or those named lists. And basically what it does is it strips it out and you're just left with those actual values, kind of similar to what we had last week for fluorophores. So at this point, we've kind of exhausted a lot what we can do for the exploration on X-verse as far as that matrix value. So let's go back and look down as far as what we have on our right sidebar, see if we have any additional information that can be gained from this view instead of working through the console. So if we went ahead and clicked on the drop down for the X-verse column, we can see it becomes very much less user-friendly. So you basically will see drop-downs with square brackets, comma 1, comma 2, comma 3, going down to basically all the way down to 61. And then if you were like really trying to like compare, you could see that the values represented kind of look like the individual values for each row, but it's definitely not user-friendly and it's definitely not something I would want to work with on a given day basis. So we should probably look at something else if we're trying to like extract out the information from here. But there's one important point I want to mention because in base R, the column order can be defined by how you place a comma within the square brackets. So in this case, we kind of saw the very first column is basically designated as comma 1, with every column being designated as the position right after the comma. And the very last column in that case would be designated by the notation square brackets comma 61. So in this case, if we wanted to subset a particular value by the index location of the column name, we can do so. So in this case, we're grabbing the first column. By contrast, if we wanted to grab the last column, we could put position, comma, and then 61 to grab out that corresponding column. Now, just like we did it for a column index, no, this is a different one, sorry. Just like we just did it now, we had 1 and we had 61. But what would happen if we tried to grab a column that wasn't existing and we were using a column index? So let's go ahead and check. So in this case, we only have 61 columns, but let's say we gave it a value of 350 as its column index. We'll get back an error, kind of like we'll see in this case, with subscript being out of bounds. And this is one of those kind of errors you encounter quite frequently in R, so this is a good highlight as far as like a good point to see it. Now, just like we were able to identify a particular column based on that position within the square brackets, Can we do the same thing with rows? Yes, we can do the same thing with rows. The way we would do this is basically we need to place it in front of the comma in this case. So if we wanted the very first row corresponding to that very first cell, we would just put the 1 right before the comma, and then that would just basically subset the very first row using the base R notation at that stage. And just like we can do subsetting based on columns and subsetting based on rows, we won't go too far into it today, but we can actually select individual values based on the position of the row and the position of the column. We won't deal with this so much today, but it's useful to know in case you're trying to get at a particular cell value as far as something that you're trying to change. All right, so with that, we've covered up that very first slot within the flow frame object. We should probably move on to the next one. Let me take a sip of coffee. And we should be ready to go. All right, that very next slot we saw was a parameter slot. Now, as we're looking at it, in our right secondary sidebar, we can see it looks a little complicated already. That's because the little bit of metadata that we can see is showing it as annotated data frame object being defined by a bio-based R package and itself containing 4 slots. So seeing as the nightmare we've already encountered with the first set of it has 3 slots, it has some vague terminology that we don't necessarily understand. I know we all may be hesitant of like, do we actually have to go explore this object right now? And this is one of the things where I'm like, okay, we've made it this far into the heart of an FCS file. We're not about to call it quits. So charge, my fellow flow cytometrists. Let's see what's underneath that drop-down arrow. And what we do is we do survivor charge, and we see that there's 4 actual slots being shown. There's the var metadata, there's the data slot, there's the dim label slot, and there's a class version slot. And fortunately for us, there's already 2 grids, which means it's going to be much simpler to work with, and we're going to be able to get through those relatively quickly. So let's go ahead and tackle by clicking on that var metadata little grid box to the very far side. And what we see is, fortunately for us, var metadata is relatively simple. So when I click on that little grid, it just pops up this little tiny object that is a table kind of format. But you also see it has some names that are vaguely familiar: name of parameter, description of parameter, range of parameter, etc., etc. So it's relatively simple. It doesn't have anything below it, so it's quite easy to work with. I want to contrast versus what we saw earlier with expers, where we saw it as being a matrix type object. What we're seeing in this case is showing up as a data frame. And a data frame is a very common object type that we'll see constantly throughout the course. So this is our first encounter with one. And basically, it's like a matrix object, but it also has the ability to encode actual character values, column names, row names, a bunch of things that the matrix, which is a little bit more simpler, would not be able to show. So, as we mentioned, the names of those particular objects we got back for var data look kind of similar to what we were seeing within that initial read output. But let's go ahead and take another look at the data object directly below. And in this case, when we go ahead and click on it, we can see that what we actually saw within that initial read FCS output is what we're seeing within this particular object. So if we're trying to get the actual things that we're seeing displayed on the console, we need to extract this particular one. Now, name is kind of like intuitive. We know it's the detectors that we're interested in. The description is blank right now, but this is a raw spectral flow cytometry data. If you're working with a conventional flow cytometry file or a unmixed spectral flow cytometry file, your actual marker of interest would appear within this description column. And then range, min, and max range we'll talk about later. They're not particularly important for what we need to worry about today. So if we wanted to extract this little data frame, we're going to need to get at it as far as getting within the flow frame S4 object, and then getting within the parameters, and then grabbing the actual data that we want. So in terms of like actually writing this out, if you're trying to grab that data frame, we're basically using the accessor functions for at. So we're basically saying within flow frame, grab me the parameter slot, and then within the parameter slots, grab the data, and then assign it to the parameter data. And kind of similar to what we did, once we create this object, we can then say how many we want to actually see using the head function, and it will display those first 10 rows for that particular object type. And just like we saw with the extra slot, there is a bioconductor helper function that basically avoids all the extra hassle as far as like getting to this particular object type. In this case, it's the parameters function. And you still need to specify at data, because that's the slot within parameters you're trying to access. And in this case, just note, this is placed directly outside the parentheses, which can look a little daunting when you first see it, but that's basically, it's within that particular slot in flow frames, you're trying to grab an additional slot. And I'm just assigning this to a parameter data alternate for now. Now, if we were running structure function on that particular object, what do we end up seeing? And this is kind of typical of what we would expect to see for a data frame. So a data frame, it'll show you the number of rows by the number of columns, and then each of the columns you'll see designated by the little $sign, and then the name of the particular column. So you can see this one's name, this is description, this is range, this is min range, this is max range. So this is a very typical structure for a data frame type object. Now, if you were actually trying to grab a particular column within this data frame, you could do the base R notation with like comma 1, comma 2, comma 3, comma 4. But you can also actually use the name of the column to be able to grab a particular column of interest. And the way that this would work is we're not actually using the @ symbol, kind of like what we were doing for slot within the flow frame object, but we're going to be using a particular $sign for this. So if you were writing this out, for example, right now in your console window, parameter data @ will not actually give you any output. However, if we swap that around and use parameter data $sign, it's going to open up suggestions and start showing you the actual column names. So this is kind of the first indication as far as like, if you know it's a data frame, just know you're going to need to either use the base R notation with the comma for index designation of the column, or you will have to do like the $ symbol to like access like the actual column names within that particular object. So this is not initially intuitive. This is something that you develop over time as you become more familiar with R. Just remember, the main goal is when you're working with anything new, when you've extracted everything new, just know what kind of object it is. Because just like we are working with tools, if a data frame is like a paintbrush as far as a function goes, we need to make sure we're providing paint. So matching the function to its respective object type that it works with is the most important thing as you start initially building and navigating. And just like we saw with the matrix, we can also subset data frames by the index positioning. So in this case, if I wanted to grab the first column, comma 1 grabs that first column. All right. So at this point, we're still very much perplexed as far as like what's going on with this $P certain number as far as the indications go. We still haven't got the actual answer of what it does, but we kind of see it's matching individual detectors across different types of locations within the larger flow frame objects. So we're getting some context that it's at least linking the different things together in some particular way. And I think I went through these a little bit earlier. Description is where you would see the actual name being shown for the particular marker of interest, depending on what you assign to that floor. And range, min range, and max range are not things you're going to encounter regularly. I will note if you're actively messing with the system and you change these values, if you export it out to a new FCS file, you'll see it looks very wonky in FlowJo or FCS Express because these values are kind of used to like zoom in appropriately on your population of interest. So when you start dramatically changing these numbers, wonky things can happen. So. At this point, however, we've looked under the var metadata slot, we've looked under the data slot, we've seen both of the matrices associated with them, we saw the only information that we can use from it, so at this point we can go ahead and tackle those last two slots remaining within parameters. And the first one is dim labels, and fortunately when we click on it, not very much is returned. It just gives us the actual labels of row names and column names. So it seems to be something internal, it's not something we need to worry about. Yay, we can continue and move on. And then there's that last slot. We click on it, fearing the worst, and we're just fortunate enough that it just gives us annotated data frame and a particular version of what kind of object specification it is. So these are both very much internal, never going to be something we ever have to encounter again. So the main things we've encountered are the expers values, which are our MFI values for a particular flow frame, and maybe that data frame within parameters, which also includes like the names of our particular detectors, potentially the names of our markers. Those are the kind of information that we would need to retrieve from the FCS file. So with this being mercifully short, at this point we're now down to 2 of the 3 slots in the original flow frame object, so we just have to tackle the very last one, which is description. So if we are working within positron and we're still doing our exploration, we can do that last drop-down arrow for description. And what we see is a very large list immediately materializes. Now, you could go ahead and scroll down all the way down the list, but we also know from that first initial read.fcs function readout that it's likely going to be at least 499 objects long. Now, there's no reason in the world we need to know the location of all these little keyword objects at that point, but it's at least useful to know some of the big picture as far as what they are doing. So there has to be a better way of actually being able to look through this to kind of parse what's going on rather than just have to scroll all the way down a huge massive list. So if we were trying to do this, if we just wanted to retrieve the data and assign it to a particular object, which we can then subset and look at individual ones independently, we're going to need to do that same kind of approach of getting anything out of a slot within the flow frame, which is using that @ symbol. So in this case, we do flow frame @ description, which is basically grabbing this list and we're assigning it to the description list object in our environment. And sure enough, it forms. And let me see if I can actually scroll all the way down. Yeah, I can start scrolling. My monitor's not liking this. Yeah, all the way down. So it's very much a very large list that we're not going to be able to work with directly. So at least we have the values out. We can then deal with them individually as we go. So the list is a little bit too large for what we need. We need to be able to subset it down. Yes, we can use the head function. So if you did head the particular list, give us the first 5, it'll give us the first 5 actual keywords that are present within the list. Another way we could do it is potentially if we could subset it based on position. So the way you would subset it based on position, kind of what we saw a little bit last week, is basically if you include the colon, it'll grab from the first item in the description list through the 10th item in the description list. In this case, we can get this return back. And as we can see, this is relatively on the smaller end. My monitor is not acting up quite as much, and we have at least this initial set of information, and we can kind of see, yeah, this looks like keywords objects. I can see this is like cytometer for an aurora. I can see the date, which is probably the acquisition date of this particular file, etc., etc. So just like we saw with experts and parameters, there's also the specialized bioconductor helper function that will grab that same information for us without having to do the @ symbol. In this case, this is the keyword function, which we will actually encounter sporadically throughout the course. So if you're trying to grab just the description or the keywords list for your particular FCS file, once it's read into a flow frame, keyword flow frame to get out that particular list. And now, of course, if we run class function, just because we're checking to make sure what is this particular object, we can see that class on the description list object comes back as actual list as far as the object type that's present. So this is a little bit different from what we've been seeing for the last couple weeks in the course. So when we were talking about things and we're calling them lists last week, we're actually dealing with what's known as a vector. And vectors are still lists, but they tend to be what are known as an atomic list, which basically at the very simplest explanation just means they contain values that are all either characters, they're all either numbers, or they're all either logicals. So if we went back and looked like last week, for example, when we generated a vector, i.e. this kind of list, for floors, all these objects that were present within that particular type of list, all these objects were character objects. Similarly, we could do a set of objects that are all going to be numeric. And in a similar way, we can generate them all as being logical, so either true or false. This class type list object that we see doesn't have that constraint of everything has to be of a certain atomic type. It can include things that are numers, it can include things that are logicals, it could include individual matrices, individual data frames. A list is very gregarious in terms of like what kind of objects can be placed within that list, versus if you're trying to assign something to a vector, it's very, very finicky and it will only take things of the same object type. So what this actually looks like when we go in and check is basically you can also create a list that's actually these individual little vectors. So for example, last screen here, I created 3 vectors. I created the floors containing the name of our floors, a panel antibody counts containing the antibody counts for particular panels, and a specimen index to keep. All these 3 are what we know as vector lists, and then these can be combined together using a list function which you can kind of see will give an output kind of similar to what we just saw for that last one. And in this case, it shows you a list of tree, and then you can see this one contains 4 objects, 4 values within it, and its character. 7 values present, and it's numeric, and 4 values, and it's illogical. Now, if we went back and checked what we saw for the description list, you can see it looks similar, but it looks a little bit different. So when we look at our description list we grabbed from our flow frame, we see it's character, 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 so most of these are character values, but then there's this intermediate section here with like the actual keywords themselves, which if we go back to that list we had just generated, we seem to be missing that particular section of the field. So we're trying to like get our minds around like what's going on in this particular section. But then we can remember we did encounter that named vector earlier that had like the actual $P particular number ends afterwards. So the question is, are we missing assigning names when it came to that list that we had just created? So we can go back and double check. So in this case, if we had set up the list, but we had provided an actual name and then assigned our actual little vectors to it, would it come up with that same kind of structure? And sure enough, it does come up with that exact same structure that we're seeing for a description. So basically, within our list, we now have a name for a particular value, for a particular vector within that list, and then the actual values that are present at that point. So why would this be useful as far as having a vector within a list have an actual name? Well, rather than then have to actually subset based on a arbitrary position that you may not know right off the bat. It might be the first, it might be the third, it might be the 500th and second. How do you actually figure this one out? Well, if you have them as an actual named object in your list, you can just use our little $ accessor, and then just like start writing out the actual name of the particular value that you want, which is why lists are quite useful when it comes to R. So in this case, for the one that we just created, we might want to grab the panel antibody counts. Versus if we're working within those keywords, we might want to grab cytometer, we might want to grab operator, different things of that sort. And of course, everything that's within a list, we can still sort based on index position, because everything can be sorted by index position in R. So at this point, a lot of us are probably thinking back, and when we read .fcs files, we saw 599 keywords appear. And we definitely have that deathly fear that I'm going to start rattling off 599 different keywords, and we're all going to be here through at least tomorrow. Fear not, we are not going to do that. I would not do that to myself, much less to do that to everybody else. I just want you to navigate some of this keyword madness and just kind of get a big picture of like the different kind of chunks that are present within the keyword list of our FCS files, just so if we ever need them at some point in the future, you kind of go, yeah, I have a vague recollection of seeing something like that somewhere in the FCS file keywords, and you can go back and check at that point. So if we look at this very first chunk, which is like the 1 through 18 section, it looks to be predominantly mostly metadata of one form or another. So this early metadata section is basically, we can see some values that are particularly interesting. So if we wanted to retrieve the time that the file was started as far as being acquired, you can see there's a keyword for that, in this case btim. Their time looks like this one was acquired just shortly before 2 p.m. Similarly, you can see what kind of cytometer was that FCS file acquired on. This will vary a little bit depending on which manufacturer made the instrument, whether they're using a $cyt or they're actually spelling out a cytometer. This is one of my main gripes as far as instrument manufacturers. They don't standardize their keywords, so there's like 3 or 4 different versions depending on who made it. You can get manufacturer serial number next time your field service engineer is asking which instrument you need to have service. There's also the standard ones you more associate as far as like when was the file acquired with the date keyword, and at what time was the acquisition stopped, and then you'll see the etim keyword. The important thing to notice for these is they actually do have a $ included in the actual keyword name, which is something I didn't initially grasp when I first started, so I constantly try to take off the $. But no, it's actually part of the keyword name is the $. That's present. And same things, additional little ones. The file name of a particular file can be retrieved. Who acquired that particular file. There's a bunch of them at that point. So that's the early metadata section of the keyword list. The next section is the largest stretch by far, especially if you're working with a spectral flow cytometry file. And you'll see it basically starts P10B, all those random P and certain numbers that we were seeing present within the read.fcs file. And you can kind of see it just continues on and on and on. It's giving the occasional detector, it's giving occasional raw fluorescence in the case of this raw spectral file. So you kind of are thinking it must have to do something with the actual detectors themselves. And fortunately for us, we don't have to dive through however many 300 different keywords that is, because they're all pretty consistent in file patterns. So you'll notice the number will change, but basically it's always a P certain number B, in this case 7, P7E, P7N, P7R, P7 type, P7V. So it's a consistent pattern that goes down and is repeated for each particular detector on a spectral flow cytometry instrument. If you were actually trying to figure out what it is, you can go to the flow cytometry standard documentation where you're actually defining how to do an FCS 3.0 or 3.1. And basically what these little letters mean is B is basically the number of bits reserved for a parameter number. In this case, it's always going to be 32 for most of them. This is something I don't touch. E is going to be the amplification type for a parameter number. It's going to appear as 0, 0. I've never really understood this well. I know it's something about the focusing on a file, because when I've changed it, FlowJo and FCS Express kind of we're not able to zoom in properly on the negative values. There's a short name for a parameter, which is what we've been seeing in that dropdown from the read.fcs file. We can see it's showing us UB6. And then there's a range for parameter number, which is that same value we saw in that initial readout. And then finally there's type. It's a raw fluorescence in this case, since it's a raw FCS file. And then detector voltage for a parameter, which is showing at 506. So, while this is a massive stretch of keywords, and it may not be immediately obvious what you can do, at least for our core, this has been particularly useful knowledge to know about. So for us, we ended up building an automated instrument QC dashboard for all the particular instruments at our core. And we have historical data for all these instruments because we've been acquiring daily QC bead files for every single instrument in our core, dating back at least 7 years. So once I figured out that I can extract the parameter name for the particular detector, as well as the actual voltage value for that particular detector, I was able to go back and look at individual files for every day, go into R, open the flow frame for that particular file, extract those 2 bits of information that I wanted for every individual detector, and then actually be able to build out an actual QC website. So you can see this is the general overview for a particular day, but the usefulness is particularly within that detector name and voltage. We can do those Levy-Jennings style plots, and then we're actually able to see changes in voltage across time. And it allows us to start pinpointing when our detectors or our lasers start to fail. So this is preempting what we're having as far as when we actually see the QC report fail for Cytec. We have at least a month warning in advance before the actual fail mark is reached. So we're able to actually go and schedule the field service engineer to come out. So it's one of those things where it's it wasn't immediately obvious when I was scrolling through the description as far as what would I ever use for the vast majority of this information. But who knows, within all these different keywords, there can be some actual things that you may want to do in the long term. And the links to the QC website are in the actual slides themselves and the website itself. So if you want to play around and see what our Aurora 5 is currently doing versus our Aurora RCS, which is always misbehaving, you can always go back and check. So yeah, the vast majority of this middle stretch of detector keywords never changes. It's that same set of 6 that are defining basically each individual keyword. The things that do change is for your forward scatter and your side scatter parameters. It obviously is not raw fluorescence, so it shows as forward scatter in this case. And then for the time parameter, it won't show either of those two. It'll show up as time, but you'll notice the little range will look different for time value versus what the range of your actual acquisition files is. All right, after all that stretch of detectors, you get to a section that's basically the middle metadata, and at this point is where you start seeing the last of those little dollar signs still showing up in the keyword values. So in this case, you see things that you'd normally see when you're setting up your experiment. You see project, spillover matrix is hiding in here, so if you're ever wondering how for your conventional flow cytometer it's able to store the actual compensation data if you already set it up in Diva, It's basically stored within this little particular keyword and then attached when you actually need it. If you scroll far enough, we get past all the detectors, and then you can see the volume of acquisition, the creator, file name, area scaling factors, etc., etc. And this was just the big description for these, being able to access it. You're still using dollar signs. Also remember, if you're using a dollar sign, that's a special character in R. So you have to include tick marks around it in order for it not to be interpreted as a particular type of command. Same thing happens if you have spaces in a particular keyword name. You'd have to include the little tick marks just so it's included as a single character value when it's being searched for. In my case, I downsampled this file, so there was only 100 cells being listed. There's 30 microliters of volume that were acquired. It was a vector flow, etc., etc. So at a certain point, this little tick mark stopped because the little spaces in the column names are no longer occurring at that stage. And then at that point, it's just single character names. So tick marks are not needed, and that extra dollar sign is not present. And all the way down. And yeah, same thing. You can get a lot of metadata from there. And then the final stretch is basically, there's also information in addition to your detectors about your particular lasers. This is mostly in the form of delays, area scaling factors. Some of them will show you like laser power, depends on the manufacturer. This can also be useful as you're trying to plot it to like monitor instrument change over time. And then there's a big stretch of middle of just saying like, how are you supposed to display each detector? So generally, your raw fluorescent files are shown as a log scale versus your forward scatter, side scatter are always shown as linear. So this is one of those sections that determines how you see it in FlowJo and FCS Express. And then the very last few are just basically seeing how your threshold is set, the user setting names as far as like where your thresholds were set at, and then your window extension values as well. And then at that point, that's generally where you will see the actual keyword stop. However, I found something interesting when setting up for this course today. Basically, when you set transformation to false within read.fcs, you don't see any additional keywords past this point. And it's very much short. You only see 499. However, when you change that value and are actually setting it as a transformation equals true, we don't get all these empty slots at the very end. What we end up getting, by contrast, is much more total number of keywords. But then when we actually go to the very end of everything, you start seeing these new keywords appear where it's flow core, the particular detector max flow core, the particular detector min. So basically, flow core is setting additional keywords when you're actually transforming the value to kind of like cue in as far as like what the transformation has actually happened. So while this never seemed to be particularly relevant to what I was doing on a particular day, what I did encounter recently is there's a couple of the flow cytometry packages from Bioconductor that we'll use that when I've exported out their normalized product and brought them into like FlowJo or FCS Express, when I check keywords, those flow core keywords are also present. So what I think that's happening for those particular packages is somewhere the author forgot to include transformation as false, which is why the data for flow core parameters is being integrated into the actual final output, which is why we're ending up seeing it in FlowJo. So it's one of those things where those arguments can leave traces that you can then see later on, and it's just something to keep an eye on. All right, so we're at the top of the hour, and this has been a lot. So we had gone in and checked how to read in a flow cytometry file into R, into what's known as a flow frame object, which we saw is semi-complicated. It's an S4 object that has up to 3 slots, the expers that contains our actual MFI values, the parameters, which include some data, including the particular names of detectors and the markers associated with them. And then there's a bunch of keywords, some of them that are useful, the vast majority that you'll never touch and you'll never have to look at again. But this is the kind of the summary of the FCS file itself. This is a good example because even though it seems a little complicated right now, a lot of bioconductor packages rely on S4 objects. So having some idea of like how to navigate them and figure out what the components are can be helpful when you're trying to actually solve things around. Vice versa, all these objects are also still made out of those other types of objects that we work with. So as we saw, there was matrices, there were data frames, these particular ones that we're working with more on a day-to-day basis. So Jay, as far as which keyword stores the particular value, that's the little v keywords for the particular detector. So in this case, let me go back up. I don't have to go half the screen up. It's this one down here, for example. So for whatever particular detector you're on, so in this case, you see like it's 37 is forward scatter. You can see the voltage or the gain is 55 for that instrument on a particular day, versus 36, it was 55, so I'm guessing that was side scatter as well. So yeah, if you're trying to retrieve all the keywords, you would basically be retrieving the N value for the actual name of the detector, and then the V value for the particular gain that was associated with it. Let me not go scrolling all the way down. Let me go back down to takeaway. There we go. All right. And then continuing our analogy, every function that we've been working with is very much a tool. And the R package is a toolbox, and just like every tool in the toolbox works with the particular object type, those are the kind of things we need to consider when we're working with R objects. So we don't want to be handing a paint, the paintbrush needs paint, don't end up handing it a screw if you're trying to get it to work properly. So next week, we're going to be diving into the world of the tidyverse, which is one of those sets of R packages that made working with R much, much more simpler to deal with in the big scheme of things. Instead of having to remember index notation as far as like, is it rows before the comma or is it columns before the comma, it's a little bit easier to work around with as far as what's going on. Vice versa, we're going to continue to be working with matrices and data frames. So the main concept that we'll be going into next week is referenced in this paper that's in the here link, where we're actually like saying what makes data tidy, how do we make our lives easier in terms of like actually getting the data sets that we need. And with that, we're at the top of the hour. I will go be conscientious of your time, so I'll be closing soon. The main additional resources for today, I know a few of you would actually like to look to see what the actual keywords are as far as like what they stand for. So I included the data file standard for flow cytometry for those of you who want to do that. There's some of you who may still be trying to like understand a little bit more about the difference between a vector and a list. The R programming, I think this is a video that I linked, was much clearer for some of them as far as like coercions, so I'm including them. And then for those with some additional experience, the Hadley Wickham book for Advanced R has good discussion as far as base types versus object-oriented objects. So this is a good section to be able to tackle that. The homework problems for this week, which are the optional ones, you can submit them if you want, but even if you don't, you'll still be at the same point for the next week for the rest of the class. Everything we worked with today was for a raw spectral flow cytometry file. I provided a unmixed FCS file. You can kind of compare and contrast what has changed between them at that particular set of time. Similar story, I included a conventional flow cytometry file. I can't remember if it was a BD Canto or a BD LSR file. Just double check to see how it changed. I saw the question as far as the Cytoflex, as far as like what was exported. It could be they're saving it under a slightly different parameter name. All the ones I've encountered have some association as far as like either the gain or the voltage setting, even the Canto does. So it might be a little bit different as far as what the particular manufacturer ended up storing as. Katie, as far as does the keyword remain the same? It is remaining the same as far as I've been able to see. It doesn't seem to be changing the particular stored keyword locally. It's kind of similar to what FlowJo ends up doing when it's doing the transformations. It's not really changing it there, it's changing it within the software as far as what I've been able to tell. But as far as when I'm grabbing the parameters, it doesn't matter if we're grabbing from the Amnes, from the max, or from everybody. It's always been under like either a gain or a v function for the location. So the data is included. The question is, where is it actually at? So if you find an example where you can't actually figure it out, open a issue on a discussion page and we'll figure a way to downsample your FCS file and put it there so that I can actually look at it and we can take a look and see if we can figure it out in the keyword. And then the very last one is if you do have access to flow cytometry software, either at FlowJo, FCS Express, whatever commercial vendor of choice you have, kind of try to see if you can figure out how to access the same set of keywords and see if you're able to see within your own files anything that looks different. If you don't have access to commercial softwares, Floriada.io, which I link to the pre-course walkthrough, also has the same kind of feature to be able to explore. So these are a little bit less involved than compared to the other weeks, but this is more trying to get you familiar with things because this was quite a dense topic to go through all across the board. And with that, if you have any questions, if anything's still unclear, I'm more than happy to circle back and address any things that we need to. If not, if you need to go, I thank you for your attention. I will see you throughout the week if you have any things, questions, or issues, and the discussion side. And I hope you have a good week.